Hi, my name is Alexander Firuz, and today I'll be presenting my project on object detection. Object detection is used in many areas that affect our daily lives. One example is seen in self-driving cars, which use object detection to spot pedestrians, roadsides, and other vehicles to drive safely. Another example can be seen in surveillance systems. Security cameras use it to detect people and objects in real time, improving safety and reducing false alarms. In healthcare, doctors use object detection to find problems like tumors in medical images, helping with faster and more accurate diagnoses. Even phone cameras detect faces to allow users to unlock their phones or collect a photo album on a particular person. For all of these reasons, in this project, I wanted to explore how object detection can be used in real-world applications. By using a model like Google's SSD MobileNet 3, we can see how object detection works efficiently and how it can be applied to devices like phones, cameras, and other systems that need quick results. In class, we've worked on various robotics concepts such as grid mapping, motion estimation, and planning modules. Object detection is closely tied to these topics because it enhances a robot's ability to perceive and interact with its environment. For example, in grid mapping, robots create a representation of their environment by using laser sensors to identify obstacles in free spaces. Similarly, object detection provides additional context by identifying specific objects, such as people, furniture, or other robots, which improves both mapping accuracy and task planning. Another example of this is motion estimation. When estimating a robot's movement, we rely on inputs from sensors like GPS or odometry. Object detection can serve as another input, helping the robot adjust its trajectory by recognizing objects or landmarks as reference points. Another example is Monte Carlo simulations. We've used Monte Carlo methods to estimate the edge of a cube using noisy measurements. Object detection faces a similar challenge of dealing with uncertainty, such as occluded or partially visible objects. By improving detection reliability, we can reduce errors in robot navigation and manipulation tasks. This project connects directly to the robotics concepts we've studied in class, such as mapping, motion estimation, and planning, by showing how object detection can enhance a robot's ability to perceive and interact with its environment. Object detection is a key component of computer vision, which enables robots to interpret visual data from cameras. By combining object detection with methods like grid mapping and motion estimation, we can create robots that navigate more effectively and make better decisions based on what they see. Exploring these connections help bridge the gap between computer vision and robotics, allowing for smarter and more capable systems. In this project, I used Google's SSD MobileNet V3 model for object detection. The goal was to detect and classify objects in images and videos, focusing on accuracy and real-time performance. For image detection, the model worked well by identifying and classifying objects in static images. For example, it detected people, buses, and cars accurately, and the bounding boxes are aligned well with the objects. Video detection worked equally as well. The bounding boxes updated frame by frame, and the model could track moving objects such as cars in traffic or pedestrians walking. Here's an example. While the others worked well, the real-time detection was a step behind. Aside from people, it would regularly misclassify objects. Here's a live demo. While the results of the object detection project were promising, there were a number of challenges that became clear during testing, especially in real-time detection and when working with cluttered or complex scenes. As seen in the demo, when using the live camera feed, the model often struggled to correctly classify objects. For example, a phone was misclassified both as a clock and as scissors. A book was misclassified as a refrigerator, and a chair was misclassified as broccoli. And other objects were even missed altogether. When I held up scissors, for example, it was completely missed. This issue seemed more pronounced when objects were smaller or blended in with the surroundings. Another challenge was the duplication of detected objects, particularly in images or videos with clutter. For instance, in the image shown here, the model detected the same object multiple times. The boy's backpack was classified as a handbag twice, with overlapping bounding boxes. In the video of the busy scene, sometimes people were duplicated by the object detection, while other objects such as traffic lights were also duplicated. This duplication issue can be caused by several factors. The SSD model's multi-scale feature maps may predict multiple bounding boxes for the same object, especially when the object spans multiple scales in the image. The model's non-maximum suppression, or NMS, which is supposed to filter out overlapping boxes, may not be aggressive enough, leading to redundant detections. In video detection, this problem becomes even more noticeable when objects are in motion or when the background is cluttered. For example, the same person or object may appear with multiple bounding boxes that shift and overlap from frame to frame. The reason for this inaccurate detection is likely due to the model's priority towards speed. This comes at the cost of accuracy, particularly for smaller objects or objects that are partially hidden. For instance, in the real-time demo I recorded, when I held up scissors, the model did not detect the object at all due to its color compared to its surroundings. While working on this project, I gained a deeper appreciation for how object detection models work under the hood. In Google's SSD MobileNet v3, feature extraction uses lightweight operations to pull out details from the image at different scales. Bounding box regression calculates the position and size of objects based on predefined anchor boxes. Non-maximum suppression, or NMS, removes extra overlapping boxes and keeps only the most confident ones. This theoretical foundation helped me understand why the model sometimes produces duplicate bounding boxes or fails with smaller objects. It's a trade-off, inherent to single-shot detection models like SSD. Overall, this project gave me valuable experience in applying object detection to both images and videos. I learned how object detection works in practice, from extracting features to identifying and localizing objects. I enjoyed exploring the balance between speed and accuracy and seeing how well the system performed in detecting objects under different conditions. While the project had challenges, such as real-time misclassifications and duplicate detections, it also highlighted areas where further improvements can be made, like fine-tuning for specific tasks or enhancing detection accuracy.